For decades, you've been told the search for alien life starts in one place, the Goldilocks zone. You know the story. A planet can't be too close to its star, or it'll be a scorcher like Venus. It can't be too far, or it's a frozen wasteland. For life as we know it, a world has to be just right. It's a simple, compelling idea that took hold in the mid-20th century and was cemented by the 90s, guiding our hunt for habitable worlds for a generation. We've aimed our most powerful telescopes at planets sitting in this celestial sweet spot, dreaming of a second Earth. But what if that story is dangerously incomplete? What if the most important factor for survival has been ignored in the popular story? The truth is, a planet can be in the perfect spot and still be a cosmic graveyard. It can have all the right ingredients, only to see them scoured away by a relentless, invisible killer. The real key to finding life isn't just a star's warmth. It's the invisible shield that protects worlds from cosmic death. The Goldilocks zone is a myth. It's time to meet the real habitable zone, the magnetic field. To understand why the Goldilocks zone is obsolete, you first have to appreciate why it was so seductive. The concept, formerly called the circumstellar habitable zone, is beautiful in its simplicity. It uses the one thing life on Earth can't do without, liquid water, as the main yardstick for finding life everywhere else. Early discussions began with astrophysicists like Su Huang in 1959, but the concept was refined by many researchers, with astronomer James Casting helping to define its modern boundaries in the 1990s, giving us a concrete target. The fairy tale analogy was perfect. Not too hot, not too cold. Easy to grasp. Too close, a planet's oceans boil away into a choking greenhouse inferno, just like Venus. Too far, they freeze solid. The habitable zone, then, is the orbital band where a rocky planet could have liquid water. In our own solar system, this zone stretches roughly from the orbit of Venus to the orbit of Mars. Earth, of course, is right in the middle. We are the proof of concept. Our existence seems to validate the whole idea. And so, when we started finding exoplanets, the Goldilocks zone became the first filter we'd run them through. Is it in the zone? The media latched on. Headlines screamed about potentially habitable worlds, almost always based on just two things. The planet was roughly Earth-sized, and it orbited in that zone. Think of discoveries like Kepler 186f, hailed as Earth's cousin, or the TRAPPIST-1 system, just 40 light-years away, with 7 rocky worlds. The excitement was immense, because at least 3 of those planets were in the star's habitable zone. It felt like we'd hit the jackpot. Suddenly, the universe seemed filled with possibilities, as many as 40 billion Earth-sized planets in habitable zones. The model was logical, elegant, and useful. It gave us a treasure map, but it assumes the relationship between a star and a planet is gentle, like a campfire providing warmth. The reality is far more violent. A star isn't a calm ball of light. It's a raging nuclear furnace, spewing deadly energy into space. And being in the just right zone for temperature means nothing if your world has no defense. An unprotected planet in the Goldilocks zone isn't a cradle for life. It's a target. Every star is a chaotic, violent place. It constantly projects a stream of charged particles into space, known as the solar wind. This isn't a breeze. It's a supersonic storm of protons and electrons flying outwards at 1,000,000 miles per hour. A constant, abrasive force. But that's just the baseline threat. The real danger comes from a star's violent outbursts, solar flares, and coronal mass ejections, or CMEs. A flare is a tremendous explosion of high-energy radiation. A CME is even more terrifying. A colossal bubble of plasma and magnetic field, weighing billions of tons, hurtling through space. When this stuff slams into an unprotected planet, it's like a cosmic-scale sandblaster. The stellar wind impacts the upper atmosphere, and the high-energy particles collide with gas atoms, literally knocking them out into space. It's a process of slow, relentless erosion. Atom by atom, molecule by molecule, the atmosphere is stripped bare. This isn't just a theory. We see it happening. The James Webb Space Telescope has caught exoplanets actively losing their atmospheres. One planet, WASP 107b, is being stripped so violently it has a massive tail of escaping helium gas. It's a dramatic, visual confirmation of just how destructive a star can be. Over millions of years, this atmospheric stripping is catastrophic. The atmosphere thins out and vanishes. As the pressure drops, liquid water boils away into space or freezes. The world becomes cold, dry, and exposed, its surface bombarded with sterilizing radiation. This is the great filter the Goldilocks model ignores. A planet's location is irrelevant if it can't hold on to its atmosphere and water. It doesn't matter if the temperature is just right, if the air and water are being blasted into the void. To be truly habitable, a world needs more than warmth. It needs a shield. It needs a defense against the unceasing fury of its own star. And the secret to that defense lies deep inside a planet's core. Fortunately for us, Earth has a shield. It's called the Magnetosphere, and it's arguably the single most important feature making our planet habitable. It's an immense, invisible bubble of magnetism, our planetary force field, and our first line of defense. Where does it come from? It's born from the heart of our planet. Deep in the Earth's center is a core of molten iron and nickel. Heat flowing from the solid inner core makes this liquid churn and convect. As the Earth spins, this motion of conductive fluid gets twisted into massive currents, and moving electric charges create a magnetic field. This planetary dynamo has generated Earth's magnetic field for at least 3.5 billion years, turning our entire planet into a giant bar magnet. This is the magnetosphere. When the solar wind approaches, it doesn't hit our atmosphere. It collides with our magnetic field. The magnetosphere acts like a rock in a river, deflecting the vast majority of these deadly particles. It creates a bow shock where the solar wind is slowed and diverted. Without this shield, our atmosphere would be stripped away, our oceans would be scoured off. Life as we know it simply couldn't exist. The magnetosphere is the unsung hero that allowed life to arise and flourish in peace. You can actually see this battle in our skies. When a strong blast of solar wind hits the magnetosphere, some particles get funneled down the magnetic field lines near the poles. As they slam into atmospheric gases, they cause them to glow. The result is the aurora borealis and aurora australis. The northern and southern lights are the beautiful scars of a war being fought constantly, silently, high above our heads. So the new requirement for a habitable world is clear. It's not enough to be in the Goldilocks zone. A truly habitable planet must have a functioning planetary dynamo. It needs a molten, conducting core and a fast enough rotation. It needs its own shield. This one factor dramatically changes the search. It forces us to ask a much more fundamental question. Does that distant world have a magnetic heartbeat? To understand the consequences for a planet that loses this protection, we only need to look at our next-door neighbor, Mars. Mars is the perfect, tragic example of this principle in action. Today, it's a cold desert, with an atmosphere 100 times thinner than Earth's. But it wasn't always this way. Decades of exploration have painted a clear picture of Mars's past. We see vast, dried-up riverbeds, deltas, and channels carved by catastrophic floods. Rovers have found minerals that could only have formed in water. The Curiosity rover even found unmistakable signs of wave ripples in ancient lakebed sediments. The evidence is unavoidable. Ancient Mars was warm, wet, and had a much thicker atmosphere. It was a potentially habitable world. It had a chance. So what happened? What turned this promising world into a frozen wasteland? The answer is a planetary catastrophe. Mars lost its shield, like Earth. Early Mars had a powerful magnetic field. We know this because we can still detect its faint remnants locked in the oldest crust. But Mars is smaller than Earth, so its interior cooled much faster. As the core cooled and solidified, the dynamo slowed and stopped. The best estimates suggest that sometime around 4 billion years ago, Mars's global magnetic field vanished. With its shield gone, the planet was defenseless. The solar wind was free to slam directly into the Martian atmosphere. This is where NASA's MAVEN mission becomes the lead detective in our cosmic crime scene. Arriving in 2014, MAVEN's goal was to figure out exactly how Mars lost its atmosphere. MAVEN's findings have been revolutionary. The spacecraft has directly observed gas being stripped from the top of the Martian atmosphere by the solar wind in a process called sputtering. By measuring argon isotopes, a gas that doesn't react chemically, MAVEN scientists determined that about 65% of the argon Mars ever had has been lost to space. The same process that stripped away the argon also stripped away the carbon dioxide that kept the planet warm and the water vapor that fed its oceans. The rate of loss wasn't constant. MAVEN found that during solar storms, atmospheric escape increases by a factor of 10 or more. In the early solar system, the sun was younger and more active. meaning those storms were far more frequent and powerful. The story of Mars is a grim, cautionary tale. It proves that being in the habitable zone isn't a guarantee. Mars was in the right place, but it lacked the internal fortitude to survive. It died because its heart grew cold. Its magnetic heartbeat faded, and with it, its chance for life. This single case forces us to reevaluate every habitable planet we find. This new understanding is completely changing how we search for life. It's a fundamental shift. If you're finding this look into the real science of survival as fascinating as I do, hit that subscribe button. We're about to apply this lesson to the thousands of worlds we've found, and the results are mind-bending. The lesson from Mars rewrites the rules of the hunt. We can't just look at an orbit. We must consider the star and the planet's ability to defend itself. This new filter forces us to look at our most promising discoveries in a harsher light. Let's start with red dwarfs, the most common type of star in the galaxy, making up about 75% of the stellar population. Their habitable zones are small and close to the star. For years, this made them seem like the perfect place to look for life. But there's a dark side. Red dwarfs, especially young ones, are notoriously violent. They are flare stars, prone to unleashing superflares hundreds or even thousands of times more powerful than the sun's. A planet in the close-in habitable zone of a red dwarf is in a nightmare scenario. The pressure from the stellar wind can be immense, anywhere from 1,000 to even 100,000 times greater than what Earth experiences. Without an exceptionally strong magnetic field, its atmosphere would be rapidly eroded. Recent JWST observations add weight to these fears. While findings are still preliminary, studies of the TRAPPIST-1 planets have so far failed to find conclusive evidence of thick, Earth-like atmospheres. Worse, a 2024 study, based on modeling, suggests that the planet TRAPPIST-1e might be having its atmosphere actively stripped away by its star. It seems that for many red dwarf worlds, the Goldilocks zone is a radiation-soaked death trap. A powerful magnetosphere isn't just a benefit, it's a non-negotiable requirement for survival. So if red dwarfs are that hostile, where should we look? This new paradigm points us toward a different class of exoplanet, super-Earths. These are planets more massive than Earth, and they appear to be very common. Their greater mass is a crucial advantage. A more massive planet likely has a larger iron core and retains its internal heat for much longer than a world like Mars. This means its dynamo could run for billions of years, generating a powerful, long-lasting magnetic field. A super-Earth could have the geophysical strength to withstand its star's onslaught, protecting its atmosphere for the eons needed for life. This makes massive, rocky worlds with strong magnetic fields, orbiting stable, sun-like stars, the new prime targets. The key isn't just location, it's location plus a powerful planetary shield. This focus on magnetospheres isn't just about finding aliens, it's reshaping our own future. As we plan to send humans to Mars, we face the same problem that killed it: the lack of a global magnetic field. Astronauts on the surface would be exposed to deadly radiation, and any attempt to terraform the planet would fail as the solar wind strips the new atmosphere away. But what if we could give Mars a new shield? What if we could build one? This may sound like science fiction, but it's an idea that was formally proposed by a top NASA scientist. The concept, put forward by then-director of NASA's Planetary Science Division, Dr. Jim Green, involves placing a powerful satellite at the Mars L1 Lagrange point, a stable spot between Mars and the Sun. The proposal suggests deploying a large structure that could generate a powerful magnetic field, an artificial magnetosphere in space. This shield would be positioned upstream of Mars, deflecting the solar wind and protecting the planet. Computer simulations of the proposal suggest this shield could be incredibly effective. By stopping the erosion, the planet's atmosphere would naturally thicken over time as trapped gases are released. This would trigger a modest greenhouse effect, raising temperatures enough to potentially melt the CO2 ice at the polar cap, creating a feedback loop that warms the planet further. Other ambitious ideas exist, but the point is clear. We now understand the problem well enough to devise solutions. This line of thinking proves how central the magnetic field is to habitability. It's not just a passive factor. It's an essential system we may one day need to engineer ourselves to expand our reach. For decades, our search for life was guided by a simple story. Find the water. We looked for Goldilocks worlds, dreaming of the oceans they might hold. But that story was incomplete. It overlooked the raging tempest every star unleashes. It missed the most vital element of a living world, its shield. The tragedy of Mars, a planet in the habitable zone that died when its magnetic heart grew cold, is the ultimate lesson. The struggles of planets around violent red dwarfs reinforce it. Habitability isn't a passive state defined by location. It's an active struggle. It requires a planet to have the internal strength to generate a force field and stand against the stellar wind. The Goldilocks zone isn't the final word. It's merely the first filter. The true habitable zone, the one that really matters, is what we might call the magnetic zone, the intersection of a planet that is not just in the right place, but also has the power to protect itself. This new paradigm is focusing our search. We're looking at super-Earths with powerful magnetic hearts. We're using JWST to not just look for water, but for atmospheres under assault. We're even learning how we might one day build these shields ourselves. The search for a second Earth continues, but we're no longer just looking for a pale blue dot. We're listening for a magnetic heartbeat. So how many worlds are out there, not in the spotlight of the old Goldilocks zone, but holding strong with their own invisible shields, waiting to be discovered? The real hunt has only just begun. Thank you for joining this deep dive into the cosmos. If you enjoyed this video and want to explore more of the universe's biggest questions, please consider liking and subscribing. And now I have a question for you. Do you think we are more likely to find life on a moon of a gas giant, like Europa, or on a super-Earth with a powerful magnetic field? Let me know your thoughts in the comments below.